Greetings! Welcome to Electronic Circuits 1. I am Razavi, and this is lecture number 33. Today we will look at the MOS device again, and this time we will delve into what we call large signal operation and small signal operation, and based on these two types of operation develop models for circuit representation of transistors. But before we go there, let's take a look and see what we did last time. In the last lecture, we went into one second order effect in MOS devices, namely channel length modulation. And we saw that as the drain voltage increases, assuming that we are already in saturation, so we are over this hump here, then what we see is that the pinch-off point actually gradually moves to the left towards the source. And that means that the actual length of the channel decreases, which according to our equation indicates that the current should increase. But rather than make L a voltage dependent quantity and making things complicated, we simply multiply the original equation by this factor of 1 plus lambda VDS. So that when VDS goes up, the drain current also increases. And that's a very simple representation that we use in many types of analysis and design. All right, we also looked at the concept of biasing. We saw that if we have a MOS device and we just apply a signal to it without anything else, the device is dead. There's no current in it. We are hoping that it will convert a voltage to a current, but it doesn't do that if we just apply a little signal to, for example, a gate source voltage, but nothing else. So what we realized was that we have to apply a certain voltage between the gate and the source even before a signal is applied to keep the transistor alive, so to speak. We saw that if we apply a certain voltage, we have a certain current, and that allows the drain current to be a sharper function of the voltage than if we are over here or if we are over here. So, in fact, this brought us to the concept of how much current change we get for a given voltage change. And that's what we might consider the strength of the device as a voltage to current converter. So we actually defined the slope to be the transconductance of the device as a measure of its strength. So what we expect is that if we bias the device at a higher voltage, higher VGS, in the absence of a signal, which means we also have a higher current, perhaps, then the transconductance is higher because this is a nonlinear equation, right? It's a nonlinear equation. So because of this nonlinearity, the slope, because of the second order effect, the power of 2, this slope keeps increasing as VGS increases. And that tells us that a higher bias voltage for gate source gives us a higher current and a higher slope. All right. So today we will delve into GM a little more and try to understand its properties. As I mentioned last time, we have 3 different expressions for GM. We simply take the derivative of the current with respect to VGS. We take the derivative of this, and the first equation that we find is this. So GM expressions. So we saw that if we take the derivative, this 2 cancels this 1/2, and then we just have mu n C ox W over L times VGS minus VTH. All right, so that's one equation that we can use. Mu n C ox W over L VGS minus VTH. But there are other manipulations that we can perform to obtain other types of expressions. For example, I know here that VGS, if I divide both sides by VGS minus VTH and multiply both sides by 2, on this side I have 2 times ID over VGS minus VTH. And on this side, I have mu n Cox W over L, VGS minus VTH, which happens to be GM. So GM is also equal to 2ID over VGS minus VTH. Okay. And lastly, what I can do is I can just remove this VGS, substitute for this VGS minus VTH from this equation. So VGS minus VTH is equal to this divided by this square root of that, right? So I replace this VGS minus VTH with that, and that gives you the third equation, which is 2 mu n Cox W over L times the bias current, the drain current. Okay, now if you look at these carefully, something looks to be a little strange. For example, here, GM is proportional to VGS minus VTH, whereas here it is inversely proportional to VGS minus VTH. Which one is correct? Well, both are correct, but it just depends on what we are doing. So let's go back to this equation and understand that there are three parameters under the designer's control that are related by this equation. W over L is one parameter, VGS minus VTH is the second one, and ID is the third one. These three are related by this equation. Mu n Cox is a constant of the technology. We don't have much control over that. So when we are looking at these dependencies and we want to know how GM varies with this or this, we have to remember that in addition to the overdrive voltage, and in addition to W over L, there's a third parameter, ID. Or in addition to ID, and in addition to the overdrive voltage, there's a third parameter, W over L, and so on. So let me elaborate on this and see what we mean exactly. Okay, so here we can say that GM, for example, is proportional to W over L if we keep VGS minus VTH constant. So VGS minus VTH constant. Okay, that's fine, no problem. Or we can say GM is proportional to the overdrive voltage, proportional to this, if we keep W over L constant. That's fine too, nothing exciting yet, right? Okay, now let's go to this equation and see what it means. So again, we keep one of them constant. Let's say we keep ID constant. So if ID is constant, it means that I have biased the device at a current of 1 milliamp, right? It has a 1 milliamp current in it before any signal comes in, because I need a certain amount of transconductance, right? I need to be somewhere on the higher parts of the ID versus VGS curve, right? I have to be somewhere around here. So I need a certain bias current, ID 0. So that's the amount that we're assuming here. Okay, so if ID is constant, GM is inversely proportional to the overdrive. So GM is inversely proportional to the overdrive. All right, so here's the tricky part. This says that if the overdrive voltage increases, GM decreases. Okay, provided that ID is constant. So now we have to ask ourselves, we are increasing the overdrive voltage, but ID is constant. Is that possible? Is it possible to increase the overdrive voltage of a Mosfet, but keep its drain current constant? Well, we go back here. Remember, there are three parameters here. So is it possible to increase VGS minus VTH while ID is constant? Yes. We have to reduce W over L. It is possible? Yes, we can do that. So this condition is possible. We just have to be careful in terms of what it means. It means that if you are changing VGS minus VTH, in this experimentation, and you'd like ID to be constant because we're trying to see the dependence of GM upon overdrive, then implicitly we're assuming that W over L is decreased. All right? Okay, now let's consider the other case. Let's assume that the overdrive is constant, but ID is changing. So VGS minus VTH is constant, and then that means GM is proportional to ID. All right. What does this mean? So I would like to increase ID so that GM increases. That happens if I keep VGS minus VTH constant. But how can I keep VGS minus VTH constant while ID increases? All right, so we just go back to that same equation. How can I keep VGS minus VTH constant while ID increases? Well, that implicitly assumes that W over L increases. All right? So this scenario assumes that the overdrive voltage is constant, meaning you connect the battery from here to here. That's it. The constant battery, we don't touch it anymore. But then I'm trying to get a higher transconductance by increasing the current. How is that possible? The only way that's possible is by making the device wider. W has to increase, or L has to decrease. So W over L has to increase. All right? And similar observations apply to this one. I just won't go there, but I want you to know that these three are all valid. It just depends on what we're assuming constant and what's variable for each of these scenarios. Okay, so to drive these home, let's look at an example. We take a MOS device like this with a certain W over L. All right. It has some mu and Cox, and it has some threshold. Now we copy this device over here. So exactly the same type of device. So here's another type of device. Another copy of the same device. So it has the same mu and Cox, the same threshold, and the same W over L. Doesn't have to, but we choose it to have the same W over L. Now, I place these devices in parallel. And by that, I mean I connect the gates together, I connect the sources together, and I connect the drains together. All right. So, my question is, if VGS is constant, which means VGS minus VTH is constant, how does the GM of the composite device compare with the GM of one device? So let's think about that for a second. We had one device with a dimension of W over L, and it had a certain battery between the gate and the source. So it has some current and it has some GM. We can calculate it using any of these, right? Now I came along and I added another device in parallel to this device. The drains are shorted, the gates are shorted, the sources are shorted. In a sense, now these two devices are equivalent to one device with twice W. Okay? W over L here, W over L here, the result is 2W over L. And you can actually see that if you look at the MOS structure, right? So here's the MOS structure that we have developed before in 3 dimensions approximately. So this is W, this is L, and this is W. And now I take another one, exactly the same, and I place these two in parallel. So now what happens is, when these two gates are connected to each other, and this is also W, we see that it is as if the two devices are connected like so, as if the width of the device has doubled. Okay, imagine you just take this and place them next to each other. If you look at the top, it might be clearer. So from the top, this is what we have. These are the source and drain. So source and drain. This is the gate, and this is W, right? From here to here is W. And then we have another one down here, source and drain, and this is also W. And now we just short these together, right? So we short the sources together, the drains together, the gates together. So if we just bring this closer and closer to each other, these two merge, and we see that the total W is 2W. All right, so what this tells us is that we have two devices whose equivalent width is 2W. Now, if you don't like this visualization, no problem. You can just write equations and see what happens, right? So we have one current for this guy, ID1. We have another current for this guy, ID2. And because the drains are connected and the sources are connected, we have ID1 plus ID2 for the overall composite device. And they have the same VGS because the gates are shorted and the sources are shorted, right? So I write ID1 is equal to ID2 is equal to 1/2 of mu n C ox W over L VGS minus VTH squared. So that means that the sum ID1 plus ID2 is just two of these, right? So it's equal to 1/2 mu n C ox 2 times W over L VGS minus VTH squared. You realize that this 2 has to go here. It has nowhere else to go. It cannot go to this voltage. We cannot take this 2 inside as square root because they have the same VGS. This VGS is the same as before when I didn't have one device. And mu n C ox, again, is a constant of the technology. It's the same for both of these devices. So equivalently, if I want to put these two devices in a black box, the only equivalency I can create is to say the new composite device is twice as wide as each of these devices. All right? Okay. So now what happens to the transconductance of the device? Well, we write GM. We can try to use any of these. Perhaps the simplest one is this one, because we kept VGS minus VTH constant, right? They have the same voltage. We just added one more device. So GM, which was 2ID1 over VGS minus VTH. This is the old GM. Old GM meaning one device. The new GM meaning both of these are in a box. So the new GM is 2 times. Now we said that the current has doubled. So 2ID1 divided by VGS minus VTH. So we see that the transconductance is doubled. All right, so you really have to be careful when we are considering various cases as to what is kept constant and what is varied, because then you get different results. So here, because VGS is the same for one device or two devices, the overall GM is twice that of one of them. But if you did something else, you could get something else, right? For example, this equation says if W goes up by a factor of 2, GM goes up by square root of 2. All right, so you have resolved all of these in your mind to make sure there's no confusion. Very well. Let's go on to the one other question that I raised last time. I just want to make sure that you have the correct picture in mind. So let me go back to that example where we said let's build an amplifier last time, and I raised the question. So here's where we are. So let's build an amplifier. So this is what we saw. We eventually had a Mosfet, which is a voltage-dependent current source. We had a microphone. We had a battery. And the battery gave us some bias voltage to make sure we have a certain current and transconductance and all of that. And then we had a resistor because we wanted the current coming out of the MOS device to be converted to a voltage. We usually like voltages as outputs and maybe even inputs. So we pass it through a resistor. And we said, this is our output voltage. So if the microphone signal is superimposed on a voltage, when the microphone signal changes, it wiggles this current changes, the changes current flows to this resistor, this voltage changes, and that's the amplified microphone signal. But then I mentioned that we do need to make sure that the device is in saturation. In saturation, we have to have this condition, right? So the drain source voltage cannot be arbitrarily small. It has to be greater than VGS minus VTH. This has to hold before the signal comes in, and it has to hold even after the signal comes in. So at least let's make sure that it's true before the signal comes in. All right, so when we have no signal, VGS is equal to V0. Okay, so that's some amount. So let's just give numbers here. So let's say V0 is, I don't know, 0.9 volts. And let's say VTH is 0.5 volts. Okay? So what is the minimum amount of VDS that we can tolerate? This equation says it has to be 0.9 minus 0.5. So for this device to be in saturation, we require that VDS be greater than or equal to 0.4 volts. All right, if VDS is less than that, we have a problem. We are in triad region, not in saturation. Okay, now, does this circuit allow or enable this device to be in saturation? In other words, can we have this much VDS here? Well, so if we need this much VDS here, and there's a current flowing this way, where is that current coming from? This part is open, so all of this current has to come from this resistor. So we really are saying that a current is circulating here, a DC current, before any signal comes in, without a source of energy, without a battery. How could that be? It's not possible, right? If you think of this MOSFET just for a second as a resistor between source and drain, we have a resistor here, we have a resistor here. That's it, we have nothing else. How could we have a current? So this circuit does not provide VDS of this much. In fact, there won't be any current here at all. VDS will be 0. VDS will be 0. The device will be in triad region. Everything is dead. Nothing good comes out of it. Okay, so we have a problem, right? And we need to figure out what to do. All right, so I really want the VDS to be, for example, more than 0.4 volts, right, with the numbers I have chosen. Okay, so can I do this? If I want that, can I go ahead and do this? I will come along and I just put a battery, maybe right here, put a battery between the source and drain and choose that to be 0.4 volts. So now the battery guarantees that this voltage minus this voltage is 0.4 volts. So it guarantees that the device is in saturation. So is that a good idea? I'll give you 90 seconds to think about it. Okay, so what did you decide? Can we use a battery like so to guarantee VDS equals 0.4 volts? Well, yes, we could. The only problem is that now we don't have an output signal anymore, even though I am talking to the microphone. Why? Well, you can see that if there's a battery here, by definition, the voltage across the battery doesn't change. Right? That's the definition of a constant voltage source. Which means the voltage across this resistor doesn't change with time. Which means this value is always 0.4 volts. If I speak into the microphone, if I speak loudly, if I speak softly, nothing comes out, right? This is always 0.4 volts. So this battery, in a sense, has shorted out this resistor. The resistor has no role in the circuit anymore because this voltage is dominated by the voltage source. So that won't do. We have to think of something else. Okay, so we have to fix this situation, and let's draw the circuit again. With all the stuff, we have a microphone, a battery, 4 VGS, and we still need this resistor. The resistor is fundamentally necessary because the current coming out of the MOSFET has to go through a resistor to create a voltage. Right? So we need that resistor. All right, so that resistor, let's draw it like this, except that I will not connect the bottom of the resistor to here, to this common rail. I will put a battery here. Another battery, and we call this V1 for now. So now something interesting happens. Okay. All right, so let's hope that with the addition of this battery, now we have a current flowing through the device, the transistor, and we have a reasonable VDS, right? Let's hope something like this is happening. Okay, so VDS is from here to here. And the question is, can I guarantee that this VDS is 0.4 volts while this resistor is still there and the current from the MOS device is flowing through RL to generate some sort of voltage which represents the amplified version of the microphone signal? Okay, well, let's just give some numbers here just to have something to work with. So let's say this resistor is 1 kilo ohm. Let's say we are shooting for a bias current of 1 milliamp here. So we'll call this ID0 to indicate that this is the current before the microphone signal comes in, when the microphone signal is 0 volts. Okay, all right. Now, how much is VDS in this case? Well, 1 milliamp flows upward through RL. Right? It has to go this way through the transistor. So it generates a voltage. 1 milliamp times 1 kilo ohm is 1 volt. But that 1 volt is like this, plus here, minus here, because the current is going upward. So that's 1 volt. So that would be RL times ID0, positive here, negative here. Okay, so let's write a quick KVL around this loop to see what we get. All right, so we have VDS here. Then we have, if I start from this terminal, I say minus VDS minus 1 volt, which is RL times ID0, plus V1 equals 0, right? That's my KVL. So minus VDS, then I'm going this way, minus 1 volt, or this would be really minus ID0 RL, and then plus V1 equals 0. I'm interested in VDS, so we see that VDS is equal to V1 minus, I will write ID0 RL, knowing that it's equal to 1 volt right now, right? Minus 1 volt. Okay, so this says that if we have, for example, 1 volt of drop across the resistor, and we need 0.4 volts for VDS at least, then it's not that hard. We just pick V1 to be how much? So this should be 0.4 volts And this should be, we are subtracting 1 volt, right? So that means that V1 has to be 1.4 volts. So indeed, if I come in and add a battery from here to here with a value of 1.4 volts, assuming that we have 1 milliamp of current and 1 kilo ohm resistance here, then the voltage that remains for this VDS will be 0.4 volts and the transistor will be happy. All right, so this allows us to provide this proper biasing. So proper biasing of MOSFET requires some sort of voltage between gate and source when there's no signal, and some sort of voltage between drain and source, so that this condition is satisfied, right, for saturation. That means that we need a battery here and we need a battery here. So as we will see later, we can try to get rid of this battery, but this is eventually our power supply, right? It's an amplifier. It requires to draw some energy from a battery or something to amplify, and that is the source of energy for this amplifier. All right, this answers that question, and now we are ready to move on to the next topic. Okay, the next topic is large signal and small signal operation. And I want to talk about that. If you watch the bipolar videos, we talked about these before, but I'm assuming you haven't, so we'll start looking at those concepts again. All right, so large signal operation. Well, we'll start with an example just to get warmed up. So here's an example. Suppose we have something very simple like this. I have 2 batteries connected to the MOSFET, V1 here, V2 here, or sorry, I guess I call this V0 and V1. So V0 and V1, just to be consistent with the previous example. Okay, and I have this resistor tied between the source and this point. Why? Just for the heck of it. We're curious to see what happens. All right, suppose that I have everything I need to know. I have W over L, I have mu NC aux, threshold, everything else, and I would like to find the current that flows through this MOS device. All right, okay. So here's what we are trying to find, ID. So we have mu NC aux, W over L, mu NC aux, W over L. We have VTH, the threshold of the device. These are properties of the device itself. Do we have VGS? No, we don't know this gate source voltage. Why? Well, because I know V0, but then there's a drop from here to here, right? So I don't know VGS yet, and I don't know ID yet. Okay, so I have to find ID directly, or I have to find VGS and then find ID from this equation, assuming that the device is in saturation. Okay, is that difficult? No, not really. I write a KVL in this loop here. If I have a current of ID in the drain, that also ends up in the source. So we have a current of ID here, right? So that current is ID, which means the voltage drop across RS is equal to ID times RS. So now let's write a KVL in this loop here. We have this voltage, V0, is equal to this VGS, gate source voltage, plus this voltage, which is ID times RS. Okay, very simple. Now, we have 2 unknowns here, VGS and ID. Fortunately, there is a relationship between VGS and ID elsewhere. This one also gives us a relationship. So we have 2 equations and 2 unknowns, and we have to solve them, right? So let's move forward and see what we can do. I will try to find VGS from here and plug it in here, because I'm trying to find ID. So let's try to find VGS from here. In fact, this is something good to know. VGS is equal to what? We multiply by 2, divide by mu n C ox W over L, and then take the square root, and then bring the threshold to the other side. So we have 2 ID over mu n C ox W over L, and then plus VTH. Okay, that's a good equation to remember. Previously, we always found ID in terms of the overdrive. Now we find VGS in terms of everything else. Okay, so let's go ahead and plug that in here, see what happens. So that's equal to square root of 2ID divided by mu n C ox W over L plus VTH plus ID times RS. So what we do know in this equation are V0, the voltage we have applied here, and VTH and mu n C ox and W over L and RS. What we don't know is ID. So we can find ID. We can even find a closed form equation for ID if we really want to. What we would do is we take V0 to that side, we take the square root to this side. Then we square both sides and simplify and so on. We end up with a simple second order equation that we can solve. Okay, all right. The purpose of this exercise was to show you that because of this nonlinear relationship, the calculations do get a little complex as we go along. Now here it's not a big deal because we can find even a closed form equation for ID. But it's not always that easy. Let's suppose that I give you something like this. I have one device like so, and then I have another device like so. I connect a battery from here to here, resistor from here to here, another battery from here to here. This is some voltage V0, this is some other voltage V0 prime, and then a battery from here to here, which is our usual V1, right? Now this becomes substantially more complicated if you want to analyze it, because these two devices now interact here. We have some current from this guy, some current from this guy, flowing through this resistor, so it's a little messy. Okay, so things can become a little more complex. All right, so far so good. I just calculated the bias conditions here, right? I just found the current. There was no signal yet. I just found how much current I might have. Could be a milliamp, half a milliamp, 2 milliamps, some amount. All right, now let's go ahead and apply a signal on top of this bias that we have. After all, we're trying to build an amplifier, so a signal should be coming in, and we're curious to see what the signal does. So let's go ahead and add a signal and see what happens. So let's add a signal. So here's the situation. I add this microphone signal here. I have the original battery of V0. This goes to the gate source of the Mosfet. And then for now, we just have a battery here. Don't worry about anything else. So we call this V1, V0. This generates a signal V mic from here to here. And then we have a certain current here, ID. So we're just interested in the drain current for now. Remember that eventually this current has to flow through a resistor, all sorts of things, but for now we're considering a very simple case. Okay, so let's imagine that V mic is just a simple sinusoid. So V mic is equal to Vm sine of omega t. That's all. It's a little sinusoid with 0 DC. It just goes up and down around 0, right? Okay. But it's added to V0. So this VGS now has V0 plus this in it, right? Okay. So can I find ID? Well, I have the same equation as before, except that V0 is replaced with V0 plus V mic. So I can say V0 plus V mic, or actually I'll just write the equation for it. V0 plus Vm sine of omega t is equal to, what did we have there? We had square root of 2id over mu n C ox W over L plus the threshold voltage, and then plus ID times RS. Okay, so we simply replace V0 with V0 plus the signal from the microphone. Okay, I'm still trying to find ID. Can I find ID here? Yes, we can find ID. Again, we have to take all of this to this side and this square root to this side. Then we have to square both sides. We end up with a quadratic equation. We solve the quadratic. We end up with some complex square roots and things in there for ID in terms of all of this. So this will go under square root and all sorts of things. It'll be a little messy. All right. So this is what we call large signal operation. Why? Because I never mentioned whether this VM is small or not. So in the general case, it might be large. So we say large signal operation if VM is not small. Now, we don't know what small means. Small with respect to what? But that's okay. For now, just assume it's not small. So by large signal operation, we mean the signal that's coming to the circuit has a certain amplitude, and that amplitude is not assumed to be small enough. Small enough for what? We'll have to see. But it's not assumed to be small. So it can be anything you want, right? It can become very large. It can be, this VM can be 10 millivolts, 15 millivolts, 100 millivolts. We haven't specified anything. If we haven't specified anything, we continue to use the complete model of the MOS device, which is ID is equal to 1/2 of mu n C ox W over L times VGS minus VTH squared. Now, if you want to include channel length modulation, then, well, times 1 plus lambda VDS. All right, so by large signal operation, that's what we mean. The signal is coming in. We don't have any particular limit on it. A common mistake by students is that they say large signal operation means DC calculations. That is not correct. They say bias calculations. That is not correct. It happens that for bias calculations, we use the large signal model, but it doesn't necessarily mean all the time that large signal means just bias. So if we have large signal operation, we use the complete model, which we call the large signal model. So we say use large signal model of the transistor. So what was the model of the transistor? You remember from last time? Well, we said that we have a gate, we have a source, not much going on between gate and source, so that's sort of open. We have a VGS, and then we have a current source here. After all, it's a voltage-dependent current source. And then here we had 1/2 of mu n C ox W over L VGS minus VTH squared. This is a drain. And if you want to include channel length modulation, then 1 plus lambda VDS. So if we don't have any restriction on the signal amplitude coming in, then we have to use this model, which we call the large signal model. All right? Okay, very good. Now, as I said, once we have a few transistors or more, things can get pretty complicated, right? Because each of these has this type of model, and then we have various devices, various currents, various voltages. We end up with a number of equations, a number of unknowns, and then many of these equations are nonlinear. so the calculations can get messy. All right. Now, under some conditions, we can simplify the situation. Okay, so we have to see what those conditions are. And those are what we call small signal operation. So let's talk about small signal operation and see what that means. Small signal operation. So as the name implies, we are hoping that in some cases, the signal that's coming in, the microphone signal, whatever it is, has a small amplitude. Again, how small is small, we have to see, but it's small. So let's see, if the signal amplitude is small, is there any simplification that we can apply to our models and circuits, etc., so that we can quickly find the properties of the circuit? Okay, so again, we start with an example. So here's what we have. We have a microphone as usual, and the battery as usual. And again, I've just simplified everything, so just have another battery here. V1, V0, V mic. And in fact, this time I don't even have, I'm sorry, there was a resistor here I forgot to draw, RS. But this time I don't have a resistor, so no RS here. Okay, so again, I know that this drain current is related to this VGS, and it just happens that now VGS is equal to the microphone signal plus V0. If you remember, that was not the case here, right? VGS was not equal to this because of the drop across the resistor, this term here. But here, it's very simple. VGS is just equal to this. So I can write ID directly. I can write ID is equal to 1/2 of mu n C aux W over L VGS minus VTH squared. By the way, lambda is 0 as usual. And VGS has a known value. VGS is the microphone signal plus V0. And the microphone signal, again, we assume to be Vm sine of omega t, right? Okay, so that's equal to 1/2 of mu n C aux W over L. I will group these a little. So I will write this as VGS minus VTH plus Vm sine of omega t squared. Now, if Vm is not small, this is it. That's how we calculate ID. No question about it. But if Vm is small, maybe we can make some simplifications. All right, so if Vm is small, what's our first reaction here? Well, maybe I can factor out VGS minus VTH to get 1 plus a small number, and then expand that using a simple approximation. Okay, so we will write this. So we say, assume Vm is much less than VGS minus VTH. And that tells us now what we mean by small. Okay, so then ID is equal to, let me actually write this down here because I need more room. So ID is equal to 1/2 of mu n C aux W over L. All right, so I will factor VGS minus VTH out of here. So what I get is VGS minus VTH squared. So VGS minus VTH squared. And then what remains inside here is 1 plus Vm sine of omega t divided by VGS minus VTH. 1 plus Vm sine of omega t divided by VGS minus VTH. Now, because this term is much less than 1, I can exploit this. 1 plus epsilon to the power of 2 is approximately equal to 1 plus 2 epsilon, right? So let's write it like that. So we have 1 plus 2 times Vm sine of omega t divided by Vgs minus Vth. So the key is that because this term over this is much less than 1, we manage to go away from this nonlinear behavior and represent the result by this simple linear expression. Okay, so let's examine this closely and see whether we can make any sense out of this. All right. Okay, so what is this? Do we know what this means, what this is here? Given that VGS, okay, sorry, let me go back here and make a small correction. I'll do it in a different color so that you remember what happened here. So here, what we really have for VGS is V0 plus V microphone, right? So this should be V0. And this should be V0. And then this should be V0. And then this should be V0. Okay, the battery, the bias value that we have for the gate source before the microphone signal comes in. Okay, so do we recognize this whole thing here? It's a current quantity, right? And it's a current quantity given by this battery. So that would be the bias current of the device, which we usually call ID0. So this is ID0, just the bias current. So let's write this and see what we get. So we have ID is equal to ID0 plus 2 ID0 over V0 minus VTH times Vm sine of omega t. So now that's not surprising. What we got is the following. The total current that flows through the transistor, ID, is equal to the bias current, of course we have a bias current, plus the signal current. The signal current is the perturbation created in the current when the signal comes in and is applied to the gate source, right? So we might call this the bias current, and we might call this the signal current. You can see that if there's no signal, if Vm is 0, there's no signal current, right? That's the perturbation that we have created inside this device here when the microphone signal goes up and down. Okay, that's very interesting. So that suggests something. Maybe when I'm considering this Mosfet here, with all the things that are going on, I can, in my mind, separate it into two separate circuits, two independent circuits. All right, so here's what we will do. We take that circuit, so let me draw it quickly again here. Sorry, let me do that with the microphone first. So we have a microphone, then we have a battery, and then we have this. And what we see is that when I'm talking to the microphone, V0, V1, then I get this total ID here, right? So I'm thinking maybe I can decompose this into two. Here's one. I have a MOS device with no signal coming in, just the bias quantities. So here's the MOS device with just the bias quantities. So we have V0, V1, a certain current, ID0. This scenario takes care of this current here. All right? And then on top of this, superimposed on this, I have another circuit, which is like this. It's taking the microphone signal and generating a certain amount of current, which is all of that stuff there. 2ID0 over V0 minus VTH times Vm sine of omega t. So in other words, what I'm really trying to do is this. I'm saying that this device consists of really two currents. One current is constant and equal to ID0. That's the bias current. And then superimposed on that, we have another current that's flowing. And that current is this guy here. So 2ID0 over VGS minus VTH times Vm sine of omega t. Okay. And what's going on here is we have a microphone signal, and then we have a battery. This represents what we have so far here. All right. Now, it's a little strange, but I guess I would need to draw this battery as well just to have a complete situation. And that's okay. We'll draw that too, V1. And that's the overall picture, right? Between the gate and the source, we don't have any impedance because the current drawn by the gate is very small. So, but we still have a voltage here, right? That's the VGS that we have. That's total VGS that we have. Okay. All right. So, one interesting observation. What is this? This factor here, is it familiar? This factor is the following. It's a bias quantity, because there's no signal in it, right? And it's equal to twice the bias current divided by the bias overdrive voltage. Because V0 is here, and when there's no signal, the gate source is equal to V0. So it's like VGS under bias conditions minus the threshold. So that's the overdrive voltage under bias conditions. So this is entirely bias dependent. It's not signal dependent, hopefully. So, and it looks familiar. Twice the drain current divided by the overdrive. What is that? Well, if we rewind and look what we obtained before, we see that it is the transconductance of the device. That's not surprising. The transconductance device says, if you give me a voltage change of delta V between the gate and source, I will give you a current change equal to Gm times delta V. Right? That is the definition of transconductance. So if we go back here, you can see if you give me a change in VGS, then I give you a change in the current equal to Gm times the change in VGS. So the microphone signal is creating a change in VGS. And as a result, we get a change in the drain current. And these are related by Gm. So it's not surprising that what we have here is just the transconductance of the device times the voltage that we have applied. So this is Gm times Vm sine of omega t. Okay, so the pen is sick again. All right, so sine of, let's see, sine of omega t. All right, so let's take a step back and see what happened here. We have a bias voltage between gate and source that gave us a certain bias current because the device is presumably in saturation. All right, then on top of that, we came in with a signal. We had a signal voltage that was applied to the gate source on top of that bias voltage, right? So signal voltage on top of the bias voltage. So this signal voltage changed this VGS, and that change got multiplied by Gm to give us a change in the current. And that's what happened. We had the voltage multiplied by Gm, and that gave us a change in the current. This current represents the change in the bias current. This is the bias current. This is the change in the current. This bias current is just from bias conditions. This is from signal conditions. So we can look at this as the change in the bias current. All right, so maybe what we can do is we decompose this according to this picture. And we say, here's one picture where we have V0, and we have a current, and we have a voltage here, V1, and this current is given by 1/2 of mu n C ox W over L V0 minus VTH squared. All right? Okay. And then, so this took care of this voltage, this current, and this voltage, because they are all bias quantities and they do not change with time. Now, next to this, we draw another circuit for this guy. What is that? Okay, that has a voltage coming from the microphone. So we draw the voltage for the microphone, V mic. And then we go to another current source, which is equal to Gm times the input voltage, the microphone voltage, right? So Gm V mic. Okay, this is the same as V mic. And then what happens to this point here? Well, this point comes back here because I am using superposition. I'm saying that this circuit plus this circuit should give me this circuit, right? So if I have a voltage of V1 between drain and source, I have to have it only in one of these two models. I cannot have it in both models. So this is what we call the large signal model, if you will, which also used for bias calculations. And this is what we call the small signal model. Small signal model of the MOS device. So it's very important to understand that small signal operation means the signal that's coming in creates a very small change in everything. In particular, it creates a small change in the overdrive voltage, because that was our condition, right? The overdrive voltage is changed negligibly as a result of this. You can see here that this term is much less than this term, so the overdrive voltage is not affected much by the voltage that's by the signal voltage. All right. Alternatively, we can say that the signal creates small changes in the drain current. So we have a bias current of, let's say, 1 milliamp, and then we have some small changes around that. These could be maybe 0.1 milliamps or something, 0.1 milliamp or something like that. So that's called small signal operation. And then in that situation, and only in that situation, can we simplify the circuit to a bias model and a signal model. And the signal model, the small signal model, consists of something that represents only changes in the current or voltage. We look at anything that is changing with time. The microphone signal changing with time has to be there. There's a component in the current of the device that's changing with time. That has to be there too. But everything that doesn't change with time, everything whose change with time is zero, is zero here, is zeroed out. So this voltage doesn't change with time. Its change with time is zero. Because we are looking for only time varying components, it's not here anymore. You see, it's not in series with this. This voltage represents a constant value. Its change with time is zero. Because it changes time with zero, it has zero value here. It becomes a short circuit. So this is what we call the small signal model. You can see that small signal model now easily lends itself to linear calculations. We don't have any, in terms of the signal itself, it's just a linear model. We don't have any square or anything else, so it's much easier to handle. All right, our time is up. I will see you next time.